Okay, we've learned how geometry is important in designing an experimental aircraft. We've also learned some steps in the aircraft design process. But there's still one more step to go. Scott mentioned earlier that the last stage in designing an aircraft is flight testing. Well, the lead center for flight testing is NASA Dryden Flight Research Center in Edwards, California. Let's take a look and see what they're doing with the HyperX.
How will the HyperX reach its test altitude?
How do the HyperX engineers collect their research information?
Why is algebra important in HyperX research?
Hi, I'm Lori Marshall. I'm a research engineer in the aerodynamics branch here at NASA's Dryden Flight Research Center. I'm one of the engineers responsible for getting the HyperX ready for flight. In order to do this, we perform tests on the vehicle to ensure that the instrumentation system will measure the necessary data. We make sure that the control room is set up properly to record this data during flight. We also perform inspections of the HyperX during assembly and testing to ensure that the systems are operational and that no damage has occurred. You see, the HyperX is a thermal protection system similar to the space shuttle. The exterior is covered with special tiles that allow it to withstand the high temperatures of high-speed flight. If any of the tiles were damaged, not only would the vehicle structure be compromised, but the aerodynamic shape that we've tested during the design process could also be altered, and this could affect the flight.
How do they flight test the HyperX at such high speeds?
Great question! The HyperX is a very small vehicle, about the size of 2 kayaks side by side. As Scott told you earlier, it will fly at about Mach 10. Now, because of its size, we only have enough fuel for use at the test conditions or when the HyperX reaches Mach 10.
How do you get HyperX to reach Mach 10?
The HyperX is attached to the nose of a rocket. The rocket is mounted under the wing of a B-52 jet. Let me explain what happens. The B-52 takes the HyperX, which is attached to the rocket, up to a preset altitude and speed, and releases it. Then, the rocket ignites and flies to an altitude of approximately 100,000 feet, traveling to the test conditions. Next, the HyperX separates from the rocket and the scramjet engine ignites. This is when the flight test begins. The HyperX generates over 600 measurements that are sent to the control room during the flight. These measurements allow the research engineers to determine the success of the flight. Each engineer can access their data on specially designed displays, which are also recorded for post-flight analysis.
How do they analyze all these data?
Well, we use several different methods, but algebra is the foundation for all of these. We use algebra throughout the design, flight testing, and post-flight analysis phases of the experiment. The vehicle stability and control system is a good example of how algebra is used during flight testing. For example, take a seesaw. A seesaw consists of a board and a pivot point, or fulcrum. Suppose we have Norbert on one side of the seesaw and Zot on the other side. Here, the seesaw is not balanced.
How do you balance the seesaw?
Well, to balance the seesaw, the product of the weight and the horizontal distance on the left side of the pivot point must equal the product of the weight and the horizontal distance on the right side of the pivot point. By moving Norbert on the left side of the pivot point closer in, you can see the seesaw becomes balanced. In mathematical terms, the weight of Norbert times his horizontal distance to the pivot point is equal to the weight of Zot times his horizontal distance to the pivot point. Now, in the case of the HyperX, the flight computer controls the wings and the tails to keep the vehicle flying and stable throughout the experiment. If not for these calculations, we wouldn't be able to fly and get the necessary data.
How do you flight test the HyperX?
As a matter of fact, we did. Unfortunately, like many experiments, this one didn't go as planned, and the HyperX never made it to the test conditions. Sometimes, when performing experiments, unforeseen events can occur. However, we were able to receive data from the HyperX before the test was terminated. We will use this data to successfully flight test the HyperX again and achieve our mission of testing scramjet technology.
Wow, if the HyperX program is so successful, how will it affect the future of flight?
Well, let's see. Recently, I flew from NASA Langley in Virginia to NASA Dryden here in California. It took about 5 hours. If commercial aircraft were using the same technology used on the HyperX, My flight time would have been reduced to 30 minutes. If you ever plan to go into space, the same technology would allow for larger cargo capacity, so space travel would cost less. This technology would also allow for reusable vehicles at a much lower cost. This means we could see more launches and more exploration of space.